Okay, so this last chapter section in chapter 8 has to do with counting principles. And there's two types of principles that we're going to be talking about today. The first one is called a permutation. So this is the definition of what a permutation is. So it says a permutation of n different elements in an ordering of the elements, such as that one element is first, one is second, and so forth. So again, a permutation is just the kind of the ordering of all of our letters or our numbers or our groups of things. Okay. So you're going to find this is actually very similar to things that we've already learned about, such as factorials. So if I ask you this first question, how many permutations are possible for the letters A, B, C, D, and F, right? So basically what I want to know is how many different ways can I group these letters? So if we remember back on factorials, right? If I want to put in my first box, right, any of these 6 letters is possible. So I know that there are 6 ways. And then once I put a letter in there, that letter now is gone. And then that means that this box will only have 5 ways. And I keep going, so forth and so on, until I fill out my boxes, right? 4, 3, 2, 1. And so we learned that we would be multiplying 6 by 5, by 4, by 3, by 2, by 1, which is the same thing as your 6 factorial, which if you have a calculator, go ahead and take that now. But if we can easily do this in our head, right, 30 times 12 times 2 should give you 720. So there's 720 different ways, right, permutations to group these 6 letters, right? So again, very similar to your factorials. So in how many ways can 8 children line up? Well, again, if I think about it, this would have 8, this would be 7, this would be 6, 5, 4, 3, 2, 1. So this is the same thing as saying 8 factorial. So 8 times 7 times 6, dot, dot, dot. So this, again, grab a calculator. This would give you 40,320. So this is when we group all of our letters. But I want you guys to note that sometimes it is useful to order a subset of that collection of elements instead of the entire collection. So what do I mean by that? Well, there's a new formula that we're going to learn about. And it looks like this. So permutation, so it says NPR, right? So it says n factorial all over n minus r factorial. So the number of permutations of n elements taken r at a time. So we're going to look at all of our letters or children as a whole, but then we're only going to look at a subgroup of them. So what do I mean by that? Let's look at an example and hopefully this will make a little bit more sense. So here's our example. 8 horses run a race. In how many different ways can these horses come in first, second, and third place? So not only am I looking at my 8 horses, so I want to know, there's 40,320 different ways those horses can come into the race. More specifically, I want to know how many different ways can first place, second place, and third place come in. So there's 3 places. So 8 is our n, it's our total number of groups, and r is that subset, right? R taken at a time, so 3 taken at a time. So we are going to say that this is 8p3. So that's what that says. So this is our total amount, and this is the top 3 places. So now everywhere I see an n, I'm going to replace that with an 8. So this will be 8 factorial all over 8 minus 3 factorial. So 8 minus 3 factorial is 5 factorial. And we've already had practice simplifying it, right? So 8 times 7 times 6 times 5. I'm going to stop with the 5 because I see a 5 factorial on the top and on the bottom. So the 5 and the 5 are going to cancel out. And all you have to do is multiply 8 by 7 by 6. So that means that there are 336 ways that the top 3 places can be determined in this 8 horse race. Okay. So why don't you guys try this next example, see if you guys can set it up. All right. So Coin Club has 5 members in it, so that is our total, right? How many different ways can a president or vice president be selected? So that means that there are 2 ways. So this should be a 5p2. So hopefully you wrote that down. So this will be 5 factorial all over 5 minus 2 in parentheses factorial. So 5 factorial all over 3 factorial. So 5 times 4 times 3. And the 3 factorials will cancel each other out. And 5 times 4 is going to leave you with 20. So there are 20 different ways that we can select a president or vice president. Now, when I select a president or a vice president, right, I might have, person A be president and then person B be vice president, which then means person B could be president and person A can be vice president. So what we want to know is, are there any distinguishable permutations? So things that are not going to repeat, right? So a distinguishable permutation is the number of permutations n objects is given by. So you have your total number of n permutations, so how many letters in a group. And then you're looking at how many times do they repeat, right? So the subscript of 1, the subscript of 2, the subscript of 3. So we're looking at all of them individually. Because if I count up n1 plus n2 plus n3 ... right, plus n of k, it should give me whatever n is. Okay, so that's what a distinguishable permutation is. So again, this example is find the number of distinguishable permutations of the groups of letters AA, EEE, JP, PR. So notice that A repeats twice. So if I make A be the first letter, right, A could also be the second letter, right? And so if I make this whole thing of A being the first letter and or A being the second letter, I might have this set of letters be in this order more than once. And I don't want that to repeat. So that means distinguishable permutations means that you only see that pattern once. Okay, so let's figure out what our n is. So our n is our total number of letters. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 9 letters total. Okay, so let's look at our n1. So I'm going to call n1a. How many a's do we have? We have 2. Our n2 would be our e. So we see 1, 2, 3. So there's 3 e's. Let's move on to the j's. There's only 1 j. There are 2 p's. And there's 1 r. So again, I should be able to add these numbers up and it should equal the number 9. So 3 plus 2 is 5. 5 plus 1 is 6. 6 plus 1 is 7. 7 plus 2 gives me 9. So that's what I was saying up here. N1, N2, all the subscripts. So now we're going to plug in all our information into this problem. So it's going to look like this. So 9 factorial all over 2 factorial times 3 factorial times 1 factorial times 2 factorial times 1 factorial. So this is n1, n2, n3, n4, n5. Okay, now I have to expand these factorials because I need to simplify. So I'm going to expand the top, 9 times 8 times 7 times 6 times 5 times 4 times 3. I'm going to stop at 3. And the 2 will be expanded to 2 times 1. I'm going to leave the 3 as a 3 factorial. 1 stays as 1, 2 times 1, and then 1. So, 1 is kind of a little redundant to write because we notice that the 1 is never going to change our answer. But the 3 factorial and the 3 factorial will cancel out. 2 times 2 gives me 4, so I can cancel out all the 4s. So again, in a calculator, if you want to multiply 9 times 8 times 7 times 6 times 5, there are 15,120 distinguishable ways that I can write these 9 letters without having to repeat. That's what that means. So why don't you pause this video and try example number 2. And how many distinguishable ways can the letters in a banana be written? All right. So we first should have counted our letters. We have 1, 2, 3, 4, 5, 6. So we have 6 letters. All right, I'm just going to jump right into writing our permutations. So I have 1b, so 1 factorial. I have 1, 2, 3 a's, so 3 factorial. And then I have 2 n's, so 2 factorial. So 6 times 5 times 4 times 3 factorial, and 1 times 3 factorial times 2 times 1. So my 3 factorials, they cancel off. I'm going to cancel that 2 off with part of that 4. And then 6 times 5 times 2 is going to give you 60. So there are 60 different ways that I can write the word banana without having to repeat. So that's what distinguishable permutations means. Now, what happens if I actually didn't care about the order of something? Well, like if I'm ordering a pizza, right? Say I wanted cheese and pepperoni, and I call Domino's or Papa John's or your favorite Pizza Hut, your favorite pizza place, and I ask, I want a cheese and pepperoni pizza. I know what I'm going to get on my pizza. I'm going to get cheese and pepperoni. If I call them up the next day, but I switch it up and I say I want a pepperoni and cheese pizza, I'm still going to get that same pizza. So the order of how I order it is not going to make a difference. So that's what combinations actually mean. Order is not important. Okay, but I can still have an example, right? I can still set it up with an equation. So the number of combinations of n elements taken r at a time. So n CR, so n factorial, and we still have the n minus r factorial. Then I have an extra r, right? Because combinations, there's going to be a different amount, right? Combinations, there's usually a smaller amount than permutations. Okay. So I'm going to show you this example the long way and why we can use this formula in order to speed up the process. So here's our first question. In how many different ways can 3 letters be chosen out of A, B, C, D, E, right? So let's think about this. I'm going to choose my first letter. So A, B, C. That's one way. It does not matter if I choose the A first, or I choose the B first, or I choose the C first. All those 3 letters are the same. So that means that I'm never going to see those 3 letters again. All right. So once I choose A and B and C, those are done. Well, if I choose A, B, what about the third letter is a D? That's a new one. Or A, B, and then E. So now I can't do any more combinations with A and B, right? Because I've done it with C, D, and E. So now I want to jump to a different set of numbers. So what happens if I just remove the B's altogether? So I say A, C, and D, right? I could do A, C, and E, right? Or I can do A, D, and E. So now I've used all of my A's in the combination. So I can't use A with B with a C. I can't use A, B, and D, and so forth and so on. So I have 6 ways. So the order doesn't matter how I choose them. So what happens if I don't ever include A, but now I have a B? Well, I haven't done B, C, and D yet, right? Or I haven't done B, C, or E yet. So I've done 1, 2, 3, and 1, 2, and 3. But those are the only letters I can use because I can't use B with A anymore because those are all taken over here. All right? Well, what happens if I don't choose C at all and I just say B, D, and E? And now those are the only letters I get to choose. If we take off A and B, the only way I can choose it is C, D, and E. So there are 3, 6, 9, 10 ways that we can choose our letters. But this is the long way. I don't want you having to sit here trying to figure out all the different ways. That's why we have an equation. Okay, so how many letters do we choose from? 1, 2, 3, 4, 5. So that is N. I'm choosing 5 letters. How many do you want to choose at a time? I want to choose 3 at a time. So my R value is 3. So this will be 5C3, which turns out to be 5 factorial all over 5 minus 3 factorial times 3 factorial. So this will be 5 factorial, 2 factorial times 3 factorial. Okay, and 3 factorial is my largest number. So I'm going to say 5 times 4 times 3 factorial 2 times 1 times 3 factorial. 3 factorials will cancel off, and the 2 and the 4 will also cancel off, leaving you with 5 times 2, which gives you 10, right? So we notice that we got 10 in both ways, right? But the equation way is going to be a little bit faster, especially if we have a larger number, all right? So that is your combination. So the thing to take away is combination order does not matter. So think about ordering a pizza or a salad, right? However you order, you know you're going to get the same thing each and every time. A permutation order does matter. So we're talking about first, second, and third place, right? President, vice president, secretary, that order does matter. That's the biggest takeaway we can talk about for permutations and combinations.